Welcome to the video. We are going to solve number of good components. So in this question, you are given a graph, okay, a graph with all the adjacency metrics along with number of edges and number of vertices, and you have to return number of good components. So a good component is nothing but a component of the graph is good if and only if the component is fully connected, which means we need to return the number of fully connected components in the given input. Okay, so see in example 1, there's only one component and that is connected with all. How it is component? Because the number of in degree is number of out degrees. See, there are, see, 1 is connected to all the nodes 3 and 2. So is 3 connected to 1 and 2. And similarly the 2 also is connected to all the remaining nodes which are 1 and 3. Hence we can say that this node 1, 2 and 3 is completely connected and hence it is a good component. So we return 1 since there is a one component which is connected. But example 2 will tell you a better picture. See, there are three components 1, 2, and 7, 6, and 3, 4, and 5. There are three components, and we need to find how many components are completely connected. So, as you can see, 6 is an individual element node. An individual node is always a good component or connected component. So, 1. Now, coming to this one 3, 4, and 5. It is similar to that what we saw in example 1. 3 is connected to 4 and 5, 4 is connected to 3 and 5, and 5 is connected to 3 and 4. Hence, it is completely connected component. So there are two total connected components. But what about 1, 2, and 7? What about 1, 2, and 7? See, 1 is connected to 2, but not with 7. 7 is connected to 2, but not with 1. Hence, it is not a connected component. So out of three given components in this example, only two of them are connected. Hence, we will return two. Okay, number of connected components. Okay, so how we'll do it? First of all, initialize a root variable. This is a root, or you can say a parent. Okay, I will initialize it. I will initialize it. Okay, as a list of integers. As a list of integers starting from 0 to v minus 1 number of vertices. Okay, then a degree, then degree I will fill with 0. Okay, it is a degree of all the components, all the nodes. Okay, so it is initialized as list of zeros of length v, which represents the degree of each vertex. Now a group, so we'll be using somewhat disjoint sets. Okay, and grouping of them. So group is initialized as this default dictionary. Okay, group just initialize a default dictionary. Fine. I will import default dictionary first. Okay, coming back. So now we will define a utility function. Utility function with an input x. So what it will do, it will, implement a union find algorithm to find the parent of a vertex. Okay, since let's say x is a vertex, so this will implement union find algorithm to find the parent of this vertex x. Cool. How it will do? Now if root of, so I'm saying it root since it will get familiar, otherwise we're looking for parent. Okay, so parent of x, if the parent of x is same as x, will return this value, otherwise call it recursively the parent, right? So this utility function will is implementing a union find algorithm to find the parent of the given node, given vertex x. Now what we'll do it, we will count the in degree and out degrees. Okay, we'll count the degrees. Okay, and union operation We'll find the degrees and apply the union operation. So first of all, we'll traverse in the given edges. Okay, ing edges. Now we'll find degree I minus 1 is 1. So here we calculated the number of degrees. Okay, we iterated throughout entire edges list, incrementing the degree of vertices which are involved in each particular edge, and then we'll perform union operations using the utility function which we just created. Okay, so here we are implementing the union function. Okay, union. After that, now that we have found out the degrees, okay, the degrees, all the degrees which were involved, and we have performed the union operation, we will group the vertices by root. We will now group the vertices by root. How will do it? First of all, so we will traverse in the entire vertices. So we have to group the vertices by root. So we traverse entire vertices on the all the vertices one by one. Then, since we created a default dictionary, okay. So now what we'll do is, and this append this side. So we are appending parent particular node, particular value of I, okay, vertex I, particular vertex I along with its parent, along with its parent. Fine. Now that we have done the union find and and applied the disjoint set, okay, unions. Now at the end we need to return the good components. Now here is a good thing. Here's a good thing. So now how will return the good components? Now our code will count the number of good components. Okay, one is the question present in this graph. So as we defined, it is a good component is a connected component where each and every vertex has a degree. Each and listen to me very carefully. Each and every vertex has a degree equal to the size of component minus 1. Size of component minus 1. This is what you have to understand. See example 2. This is small component. How many components are there in this? Nodes are there? 3. And what is the degree? 3 minus 2, which is 2. Again 4, 2, 5 and 2. So it was a connected component. See this is small single node. How many nodes are there? 1. So how many vertex it should have? 1 minus 1, which is 0. And it has 0. Thus it is a connected component. Now look at this one. How many nodes are there? 3. And how many vertex each has? 2 has 2 vertex. Apart from that, 7 and 1 has less than 2, which is 1 only. Hence it was not a connected component. So in order to be a connected component or good component, every vertex should have a degree equal to size of component minus 1. Size of component minus 1. So now we will use a generator expression within the sum to check if each component meets the criteria which we just defined. Okay, which is having vertices with degree equal to component size minus 1. Okay, so we're using generator expression. Length of component minus 1. Length of component minus 1 for all the vertices in this component. Now what is dot values. This is group dot values. Now let me submit and check the efficacy of our approach. So as you can see, it does the job pretty effortlessly in very less time. So I believe you must have learned a very good concept of disjoint sets and union find algorithm through this question. And I hope you enjoyed it. Thank you. Have a nice day.